Modification of the ITU-R P.530-17 rain attenuation prediction model. Abstract rain is the major factor that affects the propagation of signals, especially above 10 GHz frequency. To perform adequate link budget planning, the propagation impairments posed on microwave links by rain needs investigation. The ITU-R recommends a global rain attenuation prediction model for terrestrial and Earth space links, but the model is based on propagation measurement missions in temperate region, hence not suitable for tropical locations. In this study, a modification to the existing ITU-R P.530-17 rain attenuation prediction model is proposed. The modified model is implemented based on measurement data collected from 4 geographically spread terrestrial microwave DIGI MINI-LINKs operating at 15 to 18 GHz frequency. The curve fitting technique is used to modify the second constant in the ITU-R P.530-17 model to 0.743. Results suggest that for rain rates ranging from 20 mm/h to 100 mm/h, the modified ITU-R model reduced the root mean square, RMS, error value by at least 5.46%. Therefore, the modified ITU-R P.530-17 model is suitable for rain attenuation prediction in tropical climates and locations characterized by heavy yearly rain. Keywords: rain attenuation, ITU-R P.530-17, tropical climate, terrestrial link, RMS error. Introduction. The propagation of high-frequency waves, especially in rain, has become an issue for radio engineers over recent years. A microwave signal can be scattered, diffracted, absorbed, or depolarized by rain. This can restrict signal propagation, hence decrease the quality of service. Above 10 GHz, rain poses deleterious effects to terrestrial and satellite-to-Earth communication links 1, 2, 3, 4. In the design and planning of reliable communication systems, rain attenuation prediction studies become necessary. 5. The emergence and development of complex radio access networks have increased spectrum occupancy necessitated by the demand for higher bandwidths. It then becomes imperative to employ the advantages of higher frequencies that are capable of supporting these demands. 6, 7, 8, 9. Over the years, some rain attenuation prediction models have been developed by different researchers. Some key parameters used for most of the rain attenuation models include rainfall rate, frequency, specific attenuation, and elevation angle. 10. Short integration time. Rainfall rate is also one of the essential input parameters in rain attenuation prediction models. Some prediction models in South Korea have used the polynomial regression fitting method for the estimation of 1-minute rainfall rate distribution. 11, 12, 13. The major issue with recent rain attenuation prediction models is their poor performance when used in tropical countries such as Nigeria. Considerable disparities are known to exist between the measured and predicted rain attenuation values. Research has also shown that rain structures in temperate regions differ from the ones in tropical locations. Because of this, the rain attenuation prediction model described in 14 is not sufficiently accurate, hence the need for modification. Research method. Experimental procedure. Define. The rain attenuation data were retrieved from 4 DG telecommunications stations, Abuja, Plateau, Sokoto, Edo, in Nigeria, each consisting of microwave mini-link having data acquisition, retrieval, and processing system. The antennas are horizontally polarized and are strategically located in between buildings to remove interference from strong winds. The antenna is frequently sprayed with WD-40 spray to eliminate wet antenna effects. By doing this, interference from other hydrometeor sources becomes negligible. Specifications of the mini-link stations are shown in Table 1a, while the measurement site characteristics are shown in Table 1b. The signal monitoring device at the receiving stations alongside a computer system is used to monitor the signal strength at 1-minute intervals for rainy and clear sky conditions. The path attenuation is calculated by finding the difference between the received signal level, RSL, during clear sky conditions and the RSL during rainy conditions for horizontally polarized signals at various rain rates. The equation is given as follows. Weather monitoring station. The rain rate data has been obtained from a locally built rain gauge with a 0.7 mm bucket size. A small 12-watt and 6-volt solar panel are used to ensure continuous data collection and processing. The average of the 10-year rain rate data obtained from the Nigerian Meteorological Agency, NIMET, was used for the 4 sites, Abuja, Plateau, Sokoto, and Edo. The Chibal Model 17 was used to convert the 3HR rain data integration time to 1-min integration time as recommended by the ITU. Figure 1a shows the map of Nigeria containing regions of interest, while Figure 1b shows the graph of attenuation versus rainfall for the selected stations. According to the ITU-R rainfall climatic zoning, Nigeria falls in the region K with an average annual rain accumulation exceeding 2,000 mm in the south, 3,000 mm in the southeastern part, and below 1,500 mm in most parts of the north. The Nigerian climate is considered tropical and is characterized by wet and dry seasons. The wet season occurs due to northeast trade winds from November to March, while the dry season occurs due to southeast trade winds from April to. The concept of the proposed ITU-R model remains the same as the existing one. The modified ITU-R model is proposed based on the curve fitting technique with the goal of reducing the prediction error of the existing model. The root mean square error obtained from the existing ITU-R model exceeds 10%, 15, hence, the need for reduction. The modified ITU-R model is based on measured data from a tropical location. The measured values from the mini-links are used to obtain the coefficients for the new model. The rain rate for 99.99% availability is one of the variables utilized by the modified model. The percentage of time for the range 0.001 to 1 is used to determine the coefficient of the newly modified model. The curve fitting function in the Microsoft Excel suite is used to determine the coefficients of the modified model, while the solver function was used to solve the nonlinear equation of the ITU-R model using the sum of square residuals method to best fit the measured data. Hence, the coefficient that best fits the existing ITU-R model is obtained based on measured data. The measured rain attenuation value and percentage of time for a range of 0.001% to 1% are used as input data to determine the coefficients. The new coefficients obtained from the curve fitting function are significantly fit with measured data obtained from tropical climate. The second coefficient for the existing ITU-R model for prediction of attenuation for other percentages of time P is 0.6082. However, to fit the data in a tropical climate, the coefficient has been replaced with 0.743. By implementing the modified model, the percentage error and RMS error can be significantly reduced. The modified model is shown step by step from equations. The results from figures 2a and 2b show that for 0.001% unavailability, the modified ITU-R model overestimates attenuation due to rain by 5.613 dB and 5.4179 dB respectively. All models underestimated attenuation for 0.01% of time, as attenuation ranged from 9.2587 dB to 32.628 dB across all models. From figures 2c, 2d, and 2e, all models underestimate attenuation for 0.001% to 1% unavailability for reference rain rates of 60 mm/h, 40 mm/h and 20 mm/h respectively. Figures 2a suggest that for 1% of time, all three models predict attenuation with similarity, although an underestimation value of 4.12 dB was realized for the modified ITU-R and ITU-R model. The Budalal model, however, underestimated attenuation by 4.299 dB. An underestimation of attenuation by 21.761 dB and 24.718 dB was recorded for the ITU-R and Budalal model respectively at 0.001% of time. The modified ITU-R model, however, overestimated attenuation by 5.417 dB. Figure 2b further suggests attenuation ranging from 2.8178 dB to 4.615 dB for a system design of 8.77 hours a year across all models. an attenuation of 0.8017 dB going up to 0.9627 dB across all three models is estimated for a system design with 99% link availability. From Figure 2c, all three models suggest that for a system design of 5.26 minutes of outage in a year, attenuation values ranging from 10.6293 dB to 33.3658 dB is expected. This comes with an underestimation value of at least 24.1967 dB. For time availabilities of 0.01% to 1%, attenuation ranged from 0.5789 dB to 6.653 dB across all models. It was also observed from Figure 2d that the attenuation due to rainfall recorded a maximum value of 21.9838 dB for 99.999% availability and a minimum value of 6.7175 dB at 99.999% availability based on the modified ITU-R and Budalal models respectively. The ITU-R model, however, predicted attenuation of 8.6636 dB for a system design of 5.26 minutes of outage in a year. For 0.01% unavailability, the modified ITU-R and ITU-R model performed better than the Budalal model, as both models underestimated attenuation by 8.851 dB. The Budalal model, however, underestimated attenuation by 9.836 dB. For 0.1% to 1% of time, all three models predicted attenuation due to rain ranging from 0.3658 dB to 2.2621 dB. Figure 2e shows that for 0.001% of time the modified ITU-R model predicted attenuation of 10.7686 dB, which was the maximum attenuation predicted across all models. The ITU-R and Budalal model, however, predicted attenuation of 4.2438 dB and 3.0655 dB respectively. An attenuation of 0.16695 dB to 2.1473 dB across all models was realized for 0.01% to 1% of time. The accuracy of the modified ITU-R rain attenuation prediction model is tested by the root mean square value, RMS, and the percentage error measurement 20, 21, 22, 23, 24, 25, 26. The percentage error and the root mean square error are adopted to determine the measured error between the existing ITU-R model, Budalal model, and modified ITU-R model. The percentage error can be calculated by the following equation. 18. Where A predicted is the rain attenuation predicted and A measured is the rain attenuation measured at a given percentage of time. The root mean square, RMS, value can be estimated by using the mean error AAE and standard deviation E. It is given as follows. The comparison of the root mean square values for percentage of time ranging from 0.001% to 1% unavailability is shown in Table 2 to Table 6. Comparison is made between the Budalal model, modified ITU-R model, and the existing ITU-R model. From Table 2, the percentage error value of the existing ITU-R model for 0.001% of time is -68.6313%. This resulting percentage error value is slightly higher and is not preferable for tropical climates. However, from the calculations, the percentage error of the modified ITU-R model for 0.001% of time is -20.4031%. Hence, it can be shown that the modified ITU-R model significantly reduced the percentage error. For 99.99% link availability, both the ITU-R and modified ITU-R models estimated similar percentage errors of -71.0336%. The Budalal model, however, estimates a higher percentage error of -79.0765%. Results further suggest that for 0.1% unavailability, the maximum percentage error realized was -72.32%, while the minimum percentage error was -47.7332%. For 99% link availability, the minimum percentage error was -87.1235% while the maximum percentage error obtained was -90.6988% across all models. From Table 3, it is shown the ITU-R model and modified ITU-R model's performance for a system design of 99.99% and 99% availability was the same. The percentage error of a 66.8789% and -79.0009 was realized for 0.01% and 1% of time respectively. However, the Budalal model estimated a higher percentage error for time availabilities of 99 to 99.999% with percentage error ranging from -76.3285% to a 83.7181%. Table 4, Table 5, and Table 6 show that both the ITU-R and modified ITU-R model account for similar percentage errors for 99.99% availability for rain rates of 60 mm/h, 80 mm/h, and 100 mm/h respectively, while the modified ITU-R performed best for 99.999% availability when compared to the other two models as shown in Table 5. RMS values obtained from Table 7 suggest that the RMS of the existing ITU model was 75.504 for rain rate value 100 mm/h. The resulting RMS value has been reduced by the modified ITU-R model to 64.2617. Results further suggest that for rain rates ranging 20 to 100 mm/h, the modified ITU-R model reduced the RMS error value by at least 5.46135%. Conclusion. In this study, a modification to the existing ITU-R P.530-17 rain attenuation prediction technique has been developed. Based on the results, it can be concluded that the modified ITU-R P.530-17 rain attenuation model has significantly improved the prediction error of the existing ITU-R model. The new model is now suited for tropical locations and has been modified based on measured data and characteristics of rain in a tropical climate. The modified model can be implemented in different frequency bands and elevation angles for the prediction of attenuation due to rain. The new model can aid network engineers in the planning of fade mitigation techniques such as power control and site diversity. Acknowledgement. The authors wish to thank the Nigerian Multilinks Telecommunications Center, NMTC, for making their facilities available for this research.